Hello everyone, this is Kehan from Shanghai Jiaotong University. On behalf of the PandaX collaboration, it is my pleasure to present you prospects of neutrinoless double beta decay with PandaX-4T and beyond. PandaX is short for Particle and Astrophysical Xenon TPC. Since 2009, we started building PandaX-1 and 2014 PandaX-2 liquid xenon time projection chamber, both of which focused primarily on dark matter WIMP searches. Since 2019, we started working on PandaX-4T of multi-ton scale liquid xenon TPC to search for WIMP dark matter as well as neutrinoless double beta decay, the latter of which is the main topic of my presentation today. Let me note that we also started working on a R&D project to construct a 100 kg scale high-pressure gas xenon TPC to search for double beta decay with enriched xenon. PandaX is located at China Jinping Underground Lab, CJPL, in Sichuan Province, China. CJPL is the deepest underground lab in the world with 6,800-meter water equivalent overburden. The muon flux is less than 0.2 per square meter per day. It also has the advantage of horizontal access. That means large trucks can drive in large equipment easily. CJPL started as a small lab space with PandaX and CDEX dark matter experiment. Recently, it has been greatly expanded into CJPL2 as a national key science research facility for dark matter searches, neutrino physics, and astroparticle physics, etc. It has 8 large experimental halls, and PandaX occupies Hall B2. This is an overview of PandaX-4T facility at Hall B2. An extra pit was excavated in the hall, where we have our TPC inside an ultra-pure water shielding tank. The TPC active volume is about 1.2 meter in diameter and 1.2 meter high. Above the pit is a large clean room, where we assembled the detector, and now it houses electronics, DEQ, cryogenics, and circulation systems. On the left in the picture, we have the xenon distillation tower, and on the right, xenon gas system and emergency recuperation system. PandaX-4T activity at CJPL kickstarted in April 2018, when we got permission from CJPL management to start construction in the Hall B2. In August 2019, the infrastructure was completed and the detector installation started immediately. The offline xenon distillation campaign was completed in March 2020. Detector installation finished in May. By November of last year, we started taking high-quality commissioning data until April 16 of 2021. Now the detector is not running. We extracted xenon from the detector and are performing another round of offline distillation to reduce the tritium concentration in xenon. You can refer to the other 2 PandaX-4T talks at the conference for more details. This is a collection of pictures we took during commissioning. You can see that students and faculty members pose proudly in front of subsystems. The installation and commissioning were intense, but also very exciting. Data taking during TPC commissioning runs were grouped into 5 sets according to the changes in gate and cathode high voltages. We had to tweak the electrodes because of excessive discharges occurred during commissioning. We continuously monitored electron lifetime during data taking. Long electron lifetime is a good indicator for smooth run conditions and good xenon purity. In the plot in the top right corner, we show electron lifetime measured according to the shift of 164 kV peak and high-energy alpha events with respect to Z positions. For most of the data-taking periods, electron lifetime is longer than 840 microseconds, which is the nominal maximum drift time from the bottom to the top of the TPC. In 5 sets, we accumulated a total of 95 calendar days of stable data. During the first data release, the exposure we quoted is 86 days after selection cuts. More details can be found in the other PandaX-4T talks. Large natural xenon TPC can also be used for double beta decay. In our detector, we have approximately 350 kg of xenon-136, 400 kg of xenon-134, and about 4 kg of xenon-124. The liquid xenon TPC has precision 3-dimensional reconstruction, which enable us excellent discrimination power to separate a single-site and multi-site event. A large monolithic detector such as PandaX-4T has effective self-shielding power to reduce external gamma background. We can also play with visualization to optimize the search sensitivity of double beta decay. The large detector also has high signal efficiency at 90% level. The detector technology is demonstrated to have good energy resolution at Q value, which is essential for double beta decay searches. The plot showed the expected energy spectrum and background contribution before PandaX-4T took data, with assumed energy resolution of 0.8% at 2.6 MeV. The xenon-136 neutrinoless double beta decay peak shown in brown is for visual guide only. With commissioning data, we took a very preliminary look at PandaX-4T data at high energy. We found that energy resolution has been significantly improved with respect to PandaX-2. Material background still dominate, just as the figure on the right predicted. We expect the neutrinoless double beta decay sensitivity approaches XO 200 level at 10 to the 25th year with 3 years of data. This may not be as competitive as a dedicated neutrinoless double beta decay experiment, but it's a key component for multiphysics approach of PandaX-4T and liquid xenon TPC in general. We observed severe PMT saturation at PandaX-2. PandaX-4T installed newly designed PMT readout bases to mitigate this issue. For test purposes, dual readout PMT bases are also used for top and bottom center 7 PMTs. The dual readout base reads signals from a middle diode and anode of the PMT. We observed a small percentage of S1 signals out of dynamic range of digitizer and clipped. When happened to an event, only a few channels are clipped. A typical clipped S1 signal is shown in the bottom left. Large S2 signals may saturate the PMT or the base, and the pulses are distorted. In the plot in bottom right, a template pulse shown in red is compared to a saturated pulse in blue. The rising edges are aligned to calculate a desaturation factor. For 2.6 MeV events, the average correction factor for top PMT array is larger than 2, and for bottom PMT array, the correction is much smaller at about 1.04. Nominally, energy is constructed with S1 and S2 bottom charges only. Position reconstruction at high energy is greatly improved after desaturation of the top PMT array. When majority of the top PMTs of a high-energy event is saturated, the event is tend to be reconstructed wrongly in between PMTs. This is illustrated in the bottom left figure. When PMT pulses are desaturated, the distribution of calibration run events matches closely to the expectation. We do see events still incorrectly clustered more around the center 7 PMTs with dual readout bases. We are working on this issue as for now. We also found that pulses at high energy may not be defined correctly. Low energy algorithms define the end of a pulse with constant thresholds. However, at high energy, this caused signals with very long tails, and the summed charge in the tail may be more than half of the total charge, as shown in the bottom left figure. As a first step, we forced the charge integral window to 16 microseconds. For single-set events, we see energy resolution improved dramatically. With new position reconstruction, XY mapping corrections also improved, and so is energy resolution. For thorium-232 calibration run, we achieved an energy resolution of 1.5% at 2.6 MeV. I should emphasize that this is still preliminary and further improvement is expected. We were not able to process all physics data with the improvement mentioned earlier, so here I show you a very early high-energy spectrum reconstructed from S1 signal only, without the single-side cut. The spectrum is for the most central volume of half a ton of xenon only. In this small field fiducial volume, we can see that the blue 2-neutrino double-bit decay spectrum becomes prominent. With data in hand, we'll keep pushing forward to further improve energy analysis at PandaX. We are fine-tuning the charge calculation algorithms, both in terms of the effect of waveform width and the impact of desaturation. We are carrying out detailed studies on single-site and multi-site event discrimination. We are evaluating the background budget at energy with Monte Carlo simulation and inputs from calibration data. Besides the neutrinoless double-bit decay of xenon 136, we will also exploit the advantage of natural xenon TPC. We'll look into double-bit decay of xenon 134 and double electron capture related physics of xenon 124. Looking beyond PandaX-4T, we have started active R&D program on new generation of liquid xenon TPC at CJPL. Special attention will be paid to high energy at neutrinoless double-bit decay region of interest. Currently, we are exploring a few directions. Firstly, we are testing new PMTs. Currently, most of the liquid xenon TPC uses 3-inch PMTs shown on the left. We are testing a much more compact 2-inch PMT, R12699 from Hamamatsu. We are assaying PMT materials together with Hamamatsu to select low radioactivity components. The PMT can be read out in 2x2. Each one channel has an active area of 1 inch squared. It is also faster, and we expect the saturation issue disappears due to the smaller size. All the changes mentioned here will be critical for neutrinoless double-bit decay physics. We are also exploring new vessel material or revamp the traditional two-vessel design for background control. PandaX-4T will be running using natural xenon at the beginning, but we have started R&D effort on the technique of enrichment with cryogenic distillation. The picture shows the PandaX-4T distillation tower in operation. Once a hint or even a signal is observed at PandaX-4T, we will be able to run an effective beam-on, beam-off experiment with in-house enrichment program. To summarize, PandaX-4T large liquid xenon TPC has started commissioning and the data are flowing in. The detector performance at MeV range has been improved significantly compared to PandaX-2, thanks to hardware and offline analysis. It is exciting to explore double-bit decay related physics topics at PandaX-4T in the next few years. Meanwhile, we started active R&D for next generation multi-physics liquid xenon TPC at CJPL. For double-bit decay, we hope to establish PandaX as a competitive double-bit decay experiment. With an exposure of 200 ton-year of natural xenon, we will be able to explore the full inverted mass hierarchy range. Thank you very much for your attention on behalf of the collaboration. Here I show a collaboration photo we took during early this month, the collaboration meeting we discussed the PandaX-4T data analysis. Thank you.